The question is, a spherical water drop of 1 mm in diameter splits up in air into 64 smaller drops of equal size. The surface tension coefficient of water in air is 0.073 Newton per meter. The work required in splitting up the drop is A 0.96 into 10 power minus 6 joules, B 0.96 into 10 power minus 6 joules, C 0.32 into 10 power minus 6 joules, D 0.23 into 10 power minus 6 joules. Now, for such questions, you must be knowing the formula of work done in splitting up these droplets. That is the only way by which we can start our question. So, for work done formula, it is written as surface tension into change in area. So, this is what a formula we can remember. This is change in area. Change in surface area. So, in this question, surface tension is given. It is already given. So, what you need to calculate is this change in surface area. Now, for surface area calculation, you need to first calculate the diameters. So, the droplet is given 1 mm in diameter. Please be specific, because it is given diameter. If you take 1 mm radius, the answer will be changed. Now, this particular droplet is split into several smaller droplets. I have drawn 4. There are 64 smaller droplets. We don't know the radius, so we need to calculate this radius. So first, our radius is given as half mm or 0.5 mm, and we need to calculate the final radius, because for this particular droplet we know the surface area. For these all droplets, we first need to calculate radius and then we can calculate area. So, for radius, we know if this droplet is converted into 64 other droplets, the volume will still remain same, because mass conservation is happening. Density is not changing, that means volume must be same. So, initial volume is 4 by 3 pi 1 by 2 cube. We have formula for sphere is 4 by 3 pi r cube. It is formula for volume. We are using this particular formula. This will be equal to 64 times 4 by 3 pi r dash cube, because this big droplet is converted into 64 small droplets. This 4 by 3 pi will be cancelled, and this r dash cube is equal to 1 by 2 cube divided by 64. So, r dash will be equal to 1 by 2 dot 64 cube root is 1 by 4. So, r dash is equal to 1 by 8 m. This is what we wanted to calculate, because after calculation of r dash, the question is very easy. The question is, you just need to calculate change in area. Now, change in area is nothing but area final minus area initial. What is area final? Final area is 4 pi r dash square. Initial area is 4 pi capital R square. So, change in area, again we can write it as change in area is 4 pi r dash square. R dash is 1 by 8, so 1 by 8 whole square minus 4 pi r square, that is 1 by 2 square. We can write it as delta A equal to 4 pi. If we take common, then it will be 1 by 64. It is 64 times. I have made a mistake here. It is 64 times because 64 such particles are there. Again, for this particular, I will write it as 64 times area of one single droplet. So it will be 64 by 64 minus 1 by 4. So you can write it as pi. This 4 pi, here it is 1. It will become 1. 1 and 1 minus 3 by 4. 1 minus 1 by 4 is 3 by 4. 3 by 4 multiply by 4 pi. That is, so we'll get answer as 3 pi. Now, if you want to calculate work done is simple formula. Tension multiply by change in area. Surface tension is given as 0.073 and area, change in area is given as 3 pi. If you multiply these two terms, you will get final answer as 0.69. Now, this area is in mm square. The surface tension is in Newton per meter. So either you can convert this mm square in meter. So for that you need to calculate, you need to multiply this particular number by 10 power minus 6. So minus 6 joules. Because it is mm square into Newton per meter. So our final answer will be 0.69 into 10 power minus 6 joules. It is the work required. The question is, consider the following statements pertaining to stability of floating bodies. Now, the question is about floating body. First statement is, a floating body will be stable when the center of gravity is above the center of buoyancy. Statement 2 is, the positions of metacenters corresponding to different axes of rotation are generally different for the same floating object. That means the object is same, but still metacentric height may vary for different axes. Third statement is, for cargo ships the metacentric height varies with loading. Now for these three particular statements there are 4 options given: 1, 2 and 3 correct, 1, 2 correct, 1 and 3 correct, and 2 and 3 only. Now for such questions we need to attempt all the statements, so we will go for the statement number first. A floating body will be stable when the center of gravity is above center of buoyancy. Now let us take an example so that it will become very easy. If it is a floating body, then it will be immersed up to certain depth in the water or any liquid. Now whatever volume is displaced, center of that displaced volume is known as center of buoyancy. And for this particular body, if I am taking this body as normal object, then center of gravity is here. In this particular figure, the statement 1 is clearly shown, like center of gravity is above the center of buoyancy. Now we will see whether this body is stable or not. So what we can do is, we can tilt this object in the water. We have tilted this object in clockwise direction. Now we have disturbed and it is released. Now when it is tilted in this particular direction, the gravity, center of gravity will come over here, it is G dash, and center of buoyancy will remain somewhere over here, we can write it as B dash. Now if we have disturbed this object, to get stability, a reverse direction or opposite direction torque should be there, so that the body will again go to its initial equilibrium position. But here in this figure, the gravity mg is acting in downward direction, it is mg, and buoyancy force, that is buoyant force, is acting in this direction. These two forces are opposite in direction, and these two forces are creating couple in the same direction we have created the disturbance. That means the torque which should be in opposite direction is right now in the same direction we have disturbed this object. That means this object is further going to get tilted. That means this object is not stable, it is unstable. So first statement is wrong. It is incorrect statement. The statement should be a floating body will be unstable when the center of gravity is above the center of buoyancy. That is the reason why all the ships or cargo ships have very heavy loads at the bottom. What this phenomena does, it makes the center of gravity shift towards downward. So this makes this body stable, somewhat stable. So statement 1 is wrong. Now we'll go to statement number 2. Now what is statement number 2? The positions of metacenters corresponding to different axes of rotation are generally different for the same floating object. Now it is very well defined statement. Like if any object is there, like I'm having a rectangular object, it is inside water and it is floating. So there will be a center of buoyancy, there will be a center of gravity. So both the points are there, center of gravity is there, center of buoyancy is there. Now the metacenter will be somewhere over here. I am assuming metacenter is over here. Now on what parameters this metacenter depends is, we can calculate mg. It is metacentric height. It is called as metacentric height. Mg is nothing but bm minus bg. We can calculate bm and then we can calculate bg. This part is very easy. Calculating bg is very easy because it can be simply calculated by normal fluid statics. But for calculating bm or mb, there is a particular formula. That formula is I upon V. It is bm. It is height between or distance between center of buoyancy and metacentric height. Now this bm is a function of moment of inertia, and this moment of inertia depends upon axis, mass distribution, and mass. This moment of inertia depends upon these three parameters. Now for our particular statement, the position of metacenters corresponding to different axes of rotation are generally different for same floating object. It is correct. Why? Because for this particular floating object, if I am changing the axis, my moment of inertia will change. If moment of inertia is changing, bm will change, and bm is changing, that means mg will change. So statement 2 is correct. So we will write statement 2 as correct. Now we'll move to statement number 3. What is statement number 3? Statement number 3 is, for cargo ships the metacentric height varies with loading. Now it is very general statement. If we change the loading, that means we are changing the position of center of mass. If it is my ship and it is empty, it is not loaded, that means center of mass will be on its any geometrical center. Now if I load this particular ship with very heavy mass at bottom, my center of mass will shift somewhat downwards. If center of mass is shifted toward downward, that means these parameters are changed. If these parameters are changed, that means my metacentric height is going to change. So statement 3 is again correct. So for our particular question, statement 1 is wrong, 2 and 3 are correct. So do we have some option? Yeah. Option number D, 2 and 3 only. So the final answer will be D. The question is, water is coming out from a tap and falls vertically downwards. At the tap opening, the stream diameter is 20 mm with uniform velocity of 2 meter per second. Assuming steady, inviscid flow, constant pressure atmosphere everywhere, and neglecting curvature and surface tension effects, the diameter of the stream 0.5 meter below the tap opening is nearly. Now, the good news about this question is you have given all these assumptions you already wanted. So flow is inviscid, it is constant pressure everywhere, you need to neglect curvatures, surface tension effects, everything you need to neglect, and it is very simple, basic questions now. The options are A 11.7 mm, B 14.6 mm, C 17.5 mm and D 20.4 mm. This is a repeated question. The same question has been asked in engineering service and GATE. We'll see how to solve this question. Assume it is the tap opening. It is the opening of the tap, and from here this water stream is flowing. From this tap there is water stream. It is very general idea that this water stream is going to be narrow at bottom. If this is section 2 and this is section 1, it is opening and it is section 2 at which we need to calculate the diameter. So we need to calculate diameter of this stream at this end, and we are already given that the tap diameter is 20 mm. The velocity V1 is given already as 2 meter per second. So these all data given, and one more thing, the location of this point 2 is 0.5 meter below the tap opening. So from point 1 to point 2 vertical distance is 0.5 meter. Now how to calculate the diameter? We know already that whatever mass is coming out of this tap, the same mass will be going through this point 2. So mass conservation or equation of continuity, we can write it as mass in is equal to mass out, and it is per unit time. Density is same, so we can write it as discharge in is equal to discharge out. We can write it as pi into A1 square dot V1 is equal to pi, it is D1, pi D2 square into V2. In this particular equation we are given D1, we are given V1, but on this side we wanted to calculate D2, but we are not knowing what is value of V2. So first we need to calculate V2, then and then only we can calculate D2. For V2 we have Bernoulli's equation. The Bernoulli's equation can be written as P by rho G plus half V square by G plus Z is equal to constant. This is what we have equation in theorem. So for point 1 and point 2, the same equation can be written as P1 by rho G plus V1 squared by 2G plus Z1 is equal to P2 by rho G plus V2 square by 2G plus Z2. Now for Z, it is what? Potential height. So for Z1 and Z2 we need to make any one point as reference. Let us assume point 2 is my reference. That means Z2 value will be equal to 0 and Z1 will become 0.5 meter. That too positive because it is upwards. Pressure is constant, atmospheric pressure is constant everywhere, so we can cancel these two terms. We can write now equation as V1 square upon 2G plus 0.5 is equal to V2 square divided by. If I assume in this question the value of G is not given, we can take it as 9.81 meter per second square or 10 meter per second square. Since calculator is not allowed in engineering service examination, we must go for 10 meter per second square. So assuming G equal to 10 meter per second square, we can write V1 value already given, so 4 upon 20 plus 0.5 is equal to V2 square divided by 20. From here, if I multiply whole equation by 20, then 4 plus 10 is equal to V2 square and V2 is equal to under root of 14 meter per second. That means we have got velocity at this particular point. Now, if velocity is known, then diameter, simple formula. We'll apply this velocity in this formula. So, we'll get pi into what is D1 value? 20 square into V1 is 2 is equal to pi. What is value of D2 square? We need to calculate, multiply by velocity is under root 14. Now pi cancelled and we have got D2 square is equal to 20 square multiplied by 2 divided by under root of 14. You need to approximate the values because you are not having calculator. If you will approximate this answer, this D2 will come out to be 14 point something. Now this 14 point something can be 14.5, 14.6, 7. Since you have taken G as 10 meter per second square, you will get some answer near to 14.6 mm. And even if you have got 14.5 mm, the answer you should take is B 14.6 mm. So final answer will be 14.6 mm. The question is, consider the following statements regarding Bernoulli's equation. Statement 1 is, it is assumed that no energy has been supplied. Option 2, statement 2 is, the velocity of a steady stream of fluid flow will depend on cross-sectional area of the stream. Statement 3 is, consider two sections 1 and 2 along a flow stream. In these reach if Q is work done by pump and W is work absorbed by turbine, rho is density of water and G is acceleration of gravity with P, V and Z carrying standard meanings. Bernoulli's equation will read P1 by rho plus V1 square by 2G plus Z1 is equal to P2 by rho plus V2 square by 2G plus Z2 plus W plus G. Which of the above statements are correct? You need to choose which are correct statements among these three statements. Option A is 1 and 2 only, 1 and 3 only. Option C is 2 and 3 only. Option D is 1, 2 and 3. That means all are correct. So we'll check one by one. Statement 1 given is, it is assumed that no energy has been supplied. It is very true statement because Bernoulli equation is derived from energy conservation. The origin for Bernoulli equation is nothing but energy conservation. So the statement is correct that no energy is supplied, no energy is removed. In Bernoulli equation, in classical Bernoulli's equation, energy remains constant. So that means it is assumed that no energy has been supplied. Correct. The statement is right. Statement 2. The velocity of a steady stream of fluid flow will depend on cross-sectional area of the stream. Now let us see how this relation can be established. We already know that mass flow rate will be constant for steady flow. For any steady flow, mass flow rate will be constant. That means mass in will be mass out in particular given time. So rate of mass flow rate going in the system and mass flow rate coming out to the system will be same. If density is coming in the picture, then rho 1 into pi d1 square, if we are assuming that it is pipe, or we can generalize this term as area 1 A1 and V1 will be equal to rho 2 A2 into V2. Now this particular velocity, and these all terms are constant. So if I change area, velocity will get affected. So from this formula we can state that statement 2 is correct. The velocity of steady stream of fluid flow will depend on cross sectional area. Now if such statement is made like this, that the velocity of a steady stream of fluid flow will only depend on cross sectional area of stream, then such statement will go wrong. Why? Because it can also depend on density. So the statement right now given is correct because they haven't used word only, so the statement is correct. So statement 1 and statement 2, till now these two statements are correct. Now consider two sections, and we have given a modified Bernoulli equation. It is nothing but a modified form of steady flow energy equation. Such energy equation can be written as P1 by rho g plus V1 square divided by 2g plus Z1 plus Qn is equal to P2 divided by rho g plus V2 square divided by 2g plus Z2 W. So the equation given here is wrong, since Q supplied should be on intake side. So statement 3 will become wrong. So it is incorrect. So for our particular question, our answer should be statement 1 and statement 2 are correct. In options it is given option A. So our answer will be option A. The question is, an oil flows through a pipe at a velocity of 1 meter per second. The pipe is 45 meter long and has 150 mm diameter. What is the head loss due to friction? If rho, density of oil, is given as 869 kg per meter cube, and mu, that is viscosity, is 0.0814 kilogram per meter second. So the question is quite calculative. For any such question where you are not given whether the flow is laminar or turbulent and you are required to calculate the head loss due to friction, first you need to calculate whether the flow is laminar or turbulent, and to get that we have a formula called Reynolds number. Reynolds number is rho Vd divided by mu, where rho is density, V is velocity of fluid, it is average velocity, d is diameter, and mu is viscosity. So for our particular question, point till when we are not known about the fact that the flow is laminar or turbulent, we cannot apply any formula, because these two concepts are entirely different. Laminar and turbulent are two different concepts. First we need to calculate whether the flow is laminar or turbulent. So Reynolds number, to calculate Reynolds number, rho, the value of rho given as 869, velocity is given as 1 meter per second, diameter is 150 mm, that means 0.150 meter, and mu, all the units are in SI units, so mu value, that is given as 0.0814. Since you are not having any calculator, you can approximate this value. This Reynolds number will come out to be approximately equal to 1601. Now this Reynolds number is a unitless quantity, so no unit will be there. Now Reynolds number is 1601. What is significance of this number? If this Reynolds number for any pipe is less than 2000, then the flow is termed as laminar flow. Now for our particular question, is Reynolds number less than 2000? Yes, correct. 1600, it is almost 1600, so Our flow is laminar flow. Now for laminar flow, to calculate friction loss or head loss due to friction can be calculated by FLV square upon 2GD. But this is friction factor, and friction factor is not given in the question. In this whole question there is not a single word defining friction factor here. So we do have another formula, that is 32 mu VL upon rho G D square. Both formulas are same for laminar flow. So for laminar flow we can calculate friction loss by this formula or this formula. Now for the given data, 32 mu VL upon rho G D square is the suitable formula to calculate friction loss. So friction head loss will be 32 multiplied by mu. What is mu? Mu is given as 0.0814. Next, V velocity is given as 1. Length of the pipe is given as 45 meter. Next, rho is given as 869, and the value of G is 9.81. You can take it as 10 since you are not having any calculator. And for diameter it is given as 0.150 whole square. Now if you calculate this value, the final answer will be friction head loss is equal to approximately 0.6 meter. Approximately you will get 0.6. You can approximate the values, and since the options, you can see the options are quite different. Like one option is 0.51, another option is 0.61, 0.41 and 0.31. So if little bit variation is there in your answer, you can tick the correct answer. Our answer is 0.6, and the nearest option we are getting is 0.61 meters. So we can conclude that our answer is A, that is 0.61 meters. So final answer is A. The question is, consider the following statements. Statement 1, at low Reynolds number of any flow, viscous force dominate over inertial force. Statement 2, transition from laminar to turbulent flow occurs over a range of Reynolds numbers depending on the surface presented to the flow. Which of the following or which of the above statement are correct? A, 1 only, B, 2 only, C, both 1 and 2, D, neither 1 nor 2. So to solve such questions, we need to look each and every statement carefully. First statement given as, at low Reynolds number of any flow, viscous forces dominate over inertial forces. Now, to tackle this statement, first we need to know what is Reynolds number. So we'll write Reynolds number formula. Reynolds number is rho V D divided by mu. It is a mathematical term. What is meaning of this term? First we need to calculate, or first we need to know the meaning of this actual term. It is nothing but ratio of viscous force, ratio of inertial forces to viscous forces. So Reynolds number is nothing but ratio of inertial force to viscous force. It is the actual definition of Reynolds number. Now from this definition we come across this particular formula, rho Vd upon mu. It is empirical formula. Now in this particular formula, if we increase viscous force, if we increase this viscous force, due to increase in viscous force, Reynolds number will keep on decreasing. Or if we decrease this inertial force, Reynolds number will keep on decreasing. So for low Reynolds number, there are two things responsible. First, low initial forces, inertial forces, and higher viscous forces. That means these viscous forces are going to dominate over inertial forces. So statement 1 is correct. Whatever language used in statement 1 is satisfying our formula. So statement 1 is correct. Now statement 2. Statement 2 is given, transition from laminar to turbulent flow occurs over a range of Reynolds number depending upon the surface presented to flow. The first part of this statement, that transition from laminar to turbulent, itself has several Reynolds number range. That is correct. For example, if we take a pipe, for a pipe we do have a range that Reynolds number less than 2000 is termed as laminar. Reynolds number greater than 3000 is turbulent. Now from 2000 to 3000, these Reynolds number will be termed as transition flow. That is neither laminar nor turbulent. It is transition stage from laminar to turbulent. And even that particular thing depends upon the surface. One of the factor is surface roughness. This surface roughness plays very vital role in turbulent flow. In laminar flow, we usually don't care about this surface roughness, but as Reynolds number keeps on increasing, the surface roughness comes into picture and it plays very important role in turbulent flow. So it is correct that it depends upon surface presented to the flow. So statement 2 again is correct. So statement 1 and statement 2 both are correct. Option given is C. So our answer must be, final answer should be C. Hence proved. The question is, in a steady laminar flow of a given discharge, this statement is very important. For a given discharge through a circular pipe of diameter D, the head loss is proportional to. Options are given: A 1 by D, B 1 by D square, C 1 by D cube, D 1 by D power 4. It is repeated, one of the most repeated question in engineering service examination. The similar questions you would have seen in GATE also, but it is one of the favorite question because it is quite logical as well as tricky question. Let us start this question with formula of head loss. What is head loss formula? FLV square upon 2GD. Now in this formula, what I can see is velocity and diameter. From this formula, I can see that the answer should be 1 by D, but it is wrong. Why? The question is given is in a steady laminar flow of a given discharge. Now, here we do not have any term of discharge. We have term of velocity. The question is in the terms of discharge. So first we need to convert this V in discharge. But again, here we are having a coefficient, friction factor. So this friction factor, again, whether it depends on diameter or not, we are not knowing. So we need a separate formula or another formula from which we can calculate or we can establish the result. 32 mu VL upon rho G D square. Both the formulas are same. Will give same result for laminar flow. In this particular formula, again we are having velocity. Now, is there any way to convert velocity into discharge? Yes. If I multiply this numerator with area, and same divide, then this particular term, velocity multiplied by area, that is nothing but discharge. Now, I have a discharge term now. Can I write it as HF is equal to 32 mu discharge into L upon rho G D square multiplied by area? Can I write this area as pi D square by 4? Yes. Now I don't need these numerical values, but still I'm calculating everything. Now simplify this. HF is some constant, 32 pi by 4, some constant. I write it as K. It is some constant. Mu Q L upon rho G D power 4. Now this L is independent of diameter, rho is independent of diameter, G is independent of diameter, mu is independent of diameter. These all are proper. Mu is property, rho is a property, G is universal constant, length is independent of diameter, and this K is a constant term. So this whole formula I can simplify as HF directly proportional to 1 by D power 4. Do we have any option? Yes, D. Option D is given as D power minus 4. So HF or frictional head loss is proportional to D power minus 4. So we can write our answer. The statement for the question given is a two-dimensional flow field is defined as velocity vector x I cap minus y j cap. The equation of the streamline passing through the point 1, 2 is. Now you are given a velocity vector in that field, and that velocity, from that velocity vector you need to calculate the equation of streamline, and for that you are given a constraint that that particular streamline is passing through a point 1, 2. Four options are given: x plus y, x y plus 2 is equal to 0, x square y plus 2 is equal to 0, x y minus 2 is equal to 0, and x square y minus 2 equal to 0. For such question we do have a method to calculate equation or to find equation of streamline. If we are having any velocity vector given as Vx I cap, Vy j cap, then equation of streamline can be written as dx upon Vx equal to dy upon. Now from this equation and a constraint we can find equation for streamline. In our particular question, velocity is given as x I cap minus y j cap. Okay, so from this equation what we can conclude is it is Vx and it is Vy. Now can we denote or can we write these terms in this equation? Yes, definitely. So dx upon x, dy upon minus y. Do not forget the sign, it is minus y. Now can we integrate these terms? Yes. Dx by x will be equal to ln x is equal to, if I take minus common outside, it will be minus ln y plus some constant c. It is integration. Since it is indefinite integration, so there will be one constant. For this constant there is a constraint given in the question. Now if I take this term on left hand side, it will be ln x plus ln y is equal to some constant. Ln x plus ln y will be equal to ln xy is equal to some constant. Can I write this constant as ln k, so that it will be very convenient? If c is constant and k is some another constant, then ln k can be equal to c. Yeah. Now condition given is this particular streamline passes through point 1, 2. So if I put 1 and 2 instead of x and y, this equation must get satisfied. So putting 1 and 2 instead of x and y, so 1 into 2, so it will be ln 2 will be equal to ln k. So it is nothing but my constant term, c term is ln 2. So ultimately my equation becomes ln x y is equal to ln k, and what is ln k? Ln k is ln 2. So I am writing ln 2. Taking anti-log on both the sides, my equation will become x y is equal to 2 xy minus 2 is equal to 0. So do we have any option like this? Yes, correct. Answer will be C, because xy minus 2 equal to 0 is our equation of streamline. That is final answer. The question is, the center line velocity in a pipe flow is 2 meter per second. What is the average flow velocity in the pipe if Reynolds number of the flow is 800? Option is A 2 meter per second, B 1.5 meter per second, C 1 meter per second, D 0.5 meter per second. The question is very good. It is a confusing question because most of the time we do not get what he is asking, like how to calculate, how to proceed. In this question, the center line velocity or maximum velocity is given. V max is equal to 2 meter per second. In any pipe flow, if the velocity profile is laminar, then it becomes a parabolic, and this parabolic profile has its maximum velocity at its center. So we are given with this maximum velocity. Now how do we know that the flow is laminar? The Reynolds number. In this question, the Reynolds number given is 800. For a pipe flow, if Reynolds number is less than 2000, if Reynolds number is less than 2000, the flow is termed as laminar flow. And for laminar flow, such velocity profile is observed. Okay, it is center line, and from this center line our radius r is calculated, and this is V max. The question is asking the average flow velocity in the pipe. For laminar flow, average velocity is V max divided by 2. So what is V max? V max given is 2 divided by 2, that is 1 meter per second. The question is very simple, like calculation is very simple. 2 by 2 is 1. This is the final answer. But if you are not getting the meaning of Reynolds number in this question, then you won't be able to calculate 1 meter per second. So the final answer is 1 meter per second. Option is C. The question statement is, an ideal gas is flowing through an insulated pipe at a rate of 3.3 kg. There is a pressure drop of 15% from inlet to outlet of the pipe. What is the rate of energy loss because of this pressure drop due to friction? Given that R, that is gas constant, is 0.287 kilojoule per kg Kelvin, and the reference temperature T0 is 300 Kelvin. That means you need to take temperature as constant and you have to find energy loss because of pressure drop. It is nothing but work done by friction only. So the question is from thermodynamics. It is one of the most conceptual question in this paper, and I find this question difficult enough to solve if you are little weak in concept. So for this question you must realize that the energy loss asked is nothing but the work done by friction, or it is work done to overcome this friction. It is energy lost by the gas, or we can say work done by the friction on the gas. So if the gas is flowing in this pipe, it is inlet and it is outlet. We are given that there is a pressure difference of 15%. 15% pressure difference is there. So we'll find out how to calculate this thing. And apart from this, all other data given are temperature 300 Kelvin, mass given as 3.3 kg, and R as 287 joule per kg Kelvin. Now for flow system, it is a flow system. So for flow system, work done can be written as V delta P. For our closed systems, what do we write? Work done as, we write work done as P delta P. But it is open system, since it is pipe, it is an open system. For open system, work done can be written as V delta P. Now to calculate this V, we'll go for ideal gas equation, that is PV is equal to MRT. So what is V here? V is equal to MRT divided by P. Can we use this formula to replace V? Yes, of course. So we will do work done is equal to MRT upon P dot delta P. Now here mass is given, R is given, T is given, P is not given. Now the P is not given and delta P is again unknown to us. We'll write work done as M. What is value of M? 3.3 multiply by temperature is 300, R, value of R is 287. Can we write delta P by P as 0.15? Because pressure drop is given in percentage. It is nothing but 15% is nothing but delta P by P multiply by 100 is equal to 15%. So can we use this particular concept here to write delta P by P as 0.15? Yes, we can do. So next step will be 3.3 multiply by 300 multiply by 287, 0.15. So this final multiplication, this whole multiplication will come out to be 42620 something, and it is in joule per second, because it is kg per second, it is mass flow rate. So we can write it as joule or joule per second, anything you can write, because in the question it is a mistake that the mass flow rate is given as 3.3 kg. It should be 3.3 kg per second. So it will be joule per second. So final answer for work done or energy loss, work done or energy loss can be written as 42.62 kilojoule per second or kilowatt. So final answer will be A. Our answer is A, which is given 42.62 kilowatt. Question is, a jet of water issues from a sharp edged vertical orifice under a constant head of 0.51 meter. At a certain point of issuing jet, the horizontal and vertical coordinates measured from vena contracta are 0.406 meter and 0.085 meter. What is the value of coefficient of velocity? Options are given: 0.975, 0.925, 0.875, 0.825. Now, for this question, first we'll make a diagram. So assuming that this is the orifice from which water is coming out, and the head is given, the water head is given 0.51 meter. Now from this point the water will be coming outside and it will be going somewhere like this. For this particular jet, we are given the coordinates, and the coordinates are in x direction it is 0.406 meter, and in y direction it is 0.085 meters. So we are given the coordinates of the water jet at a particular instant, at any particular instant. From this we need to find the velocity, and from this velocity there is a possibility that we can find the coefficient of velocity, because coefficient of velocity is nothing but velocity actual upon velocity theoretical. Now it is the actual velocity because the jet is coming down and it is touching some coordinates, so it is actual velocity, we can write down as actual. And for theoretical velocity we have a formula root 2gh. So for theoretical we have a head that is constant 0.51, so we can write theoretical velocity as root 2 into g. For value of g I can take 10 or 9.81, anything. Since I am not having calculator, I will use 10. H, for value of h 0.51. So velocity theoretical will come out to be 3.19 meter per second. It is approximate value, you can approximate this, no issue. You can write 3.2, 3.21, anything. Now for actual velocity, how to get this actual velocity? With help of the coordinates given. For any projectile motion, it is class 11th concept, for any projectile motion, coordinate y can be expressed in terms of coordinate x. How can we do that? For coordinate x, I can write is u cos theta into t, and for coordinate y I can write as u sin theta into t plus half acceleration in y direction into t square. Here t is a variable which we want to eliminate. So what we can do, from this equation we can write t is equal to x upon u cos theta. From here the value of y will become u sin theta multiply by t. T is what? U x upon u cos theta. So I can write it as x into tan theta, because u will get cancelled, sin theta upon cos theta will be tan theta, minus half into gx square upon u square cos square theta. So it is equation of trajectory for any motion happening in 2D, motion under gravity. Here theta is equal to 0. We are assuming that the jet is horizontal at initial point, so this term will get cancelled, it will be 0. And y coordinates, if it is origin, if I assume this as 0, 0, this point will be 0.406, 0.085. So the coordinates of these points are given. The y coordinate will be negative because it is below origin. So y I can write it as 0.085 is equal to minus of half into value of g I can take it as 10, x square is 0.406 square upon cos square theta, when theta is equal to 0 is 1. So u square, that is v actual square. From this equation, from this particular equation I can solve and find v actual equal to 3.11 meter per second. So I have got theoretical velocity as well as I have got actual velocity. Now from these actual and theoretical velocities I can find coefficient of velocity, that is 3.11, that is actual velocity upon 3.19. It will be around 0.97, 0.973, 0.974, whatever it is. We have found our option near to CV, that is option A. Answer will be A, 0.975. So final answer will be A. For the next question, statement 1 is depth of center of pressure of any immersed surface is independent of the density of the liquid. Statement 2 is center of area of immersed body lies below center of pressure. Now there are 4 options. Statement 1, 2 both are correct and 2 is correct explanation of 1. Option B is statement 1, 2 both are correct but statement 2 is not correct explanation. Option 3 is statement 1 is true but 2 is false, and option D is statement 1 is false but statement 2 is true. For such questions, we'll look at both the statements very carefully because these are most confusing statement in our paper. So statement 1 is depth of center of pressure of any immersed surface is independent of density of the liquid. Let us see, the formula is H star. It is depth of center of pressure. H star is equal to x bar plus Ig sine square theta upon Ax bar. Now in this particular formula there is not a single term associated with density. So statement 1 is correct. Now statement 2. What is statement 2? Statement 2 given is the center of area of the immersed body lies below the center of pressure. No, it is incorrect. Just look at this formula. This is center of area. Now this particular term is added with something else and final term is called center of pressure. So center of pressure is more than x bar, mean depth or center of area. So statement 2 is wrong. So from the above options, from the options given, statement 2 is false. So option C, our answer will become option C. In flow through a pipe, the nature of fluid flow depends on the velocity of fluid. It is given as statement 1. Now statement 2 is Reynolds number of the fluid depends on the velocity, diameter of the pipe and kinematic viscosity of the fluid. Now these 2 statements are given and 4 options are given. We need to find which of the following option or which of these option is correct for our statements. Now if I'll go for statement number 1, it tells that in a flow through a pipeline, nature of fluid flow depends on velocity of the fluid. Now we know that for nature of fluid flow we must calculate a number that is known as Reynolds number. Reynolds number is mu, Reynolds number is rho v d divided by mu, where rho is density, v is velocity, d is diameter, mu is viscosity of the fluid or dynamic viscosity of the fluid. So statement 1 is correct because the fluid flow nature depends on Reynolds number and Reynolds number depends on velocity. So statement 1 is correct, that our nature of fluid flow depends on velocity. If it had been written that in a fluid flow through pipeline the nature of fluid flow only depends upon velocity, then the statement would have gone wrong. Right now it is correct. Statement 2, Reynolds number of the fluid depends on velocity, diameter of the pipe and kinematic viscosity of the fluid. If I'll convert this dynamic viscosity in kinematic viscosity, we'll get mu by rho, and this mu by rho is known as kinematic viscosity, so we can write it as nu. So statement 2 is again correct. Reynolds number depends on velocity, diameter and kinematic viscosity. Now to look at whether statement 2 is correct explanation to statement 1 or not. Now just look at this statement 2. It states that Reynolds number of any fluid depends on velocity, diameter and kinematic viscosity, which correctly explains that statement 1 which states that in flow through pipeline nature of fluid flow depends on velocity, because Reynolds number consists a term, a variable called velocity. So statement 2 is correct as well as it is correct explanation of statement 1. So our answer will be option number A, where statement 1 and 2 both are individually correct, as well as statement 2 is correct explanation of statement 1. So option is A.